Okay, let's get started. So, are there any questions? In general, yeah.
For the pushing, popping and pushing, so we read from the input.
Or not, yeah.
And then we pop from the stack possibly.
Yep.
And we push to the stack
Possibly. Yep.
What exactly is happening when we do like a 0, 0 epsilon?
So if we have a transition like this.
Yeah.
So remember the definition of the transition function, which I'll quickly write down. And someone pointed out that the transition function was not right in the notes, and so it's corrected to be this, to what I did in class. But it's, oops. So note that where's the reading? It's right here on the left side, and also the popping's on the left side. So the reading and the popping will determine which transitions you can apply. So if I see a 0 on the input and a 0 happens to be on top of the stack, I can apply this transition. I don't have to, but I can apply it. And if there are multiple ones of the type 0, 0 on the left, doesn't matter what I push. If there's 0, 0 on the left, I can apply any one of those transitions. I could apply others. Like, for example, if there is another transition labeled this, where I don't read, I can apply that one too, if I could apply the first one. Right? So it just determines, the two on the left determine which transitions you can apply. The push at the end is just a result of after applying the transition. But the two on the left determine whether you can apply it or not. Other questions? Yeah.
This is on problem set 6. Can we go through the process of showing if something is not copied?
We're doing that today.
Okay.
Yeah.
For problem set this is right.
Mm-hmm.
First question, can W be 0?
What do you mean by 0?
Like, can it have a length of 0?
Yeah, of course. Yeah. Well, you can always get an input or try to get an input of that size, but it's just whether that string's in the language, as W can have length 0. X can't, because then that would imply W has length -1, which is impossible. But yeah. Other questions? Who wants to see the test? All right, ready?
Yes.
It's definitely not this, but this is what you see. So there's I've blanked out all the questions. I'm just showing you the format and like the topic on each of the questions. So it's 6 questions and they're all 40 points each. The test is out of 200, and so if you do the math, that implies 40-point bonus. So. And if you happen to get over 200, you keep the bonus with you. And then option B obviously scales up just like before. Questions on the first page. And it will not be stapled. This is just for me to bring it here easily, but it will not be stapled for you. Please do not staple it again. It was no problem last time, but just as a reminder. Okay, first question. This one might look a little bit familiar. So, it's just going to be 8 subparts instead of 10 like before, where it has something to do whether something is true or not. So don't take pictures, please. It's actually an academic integrity violation, but either way. So the first 2 questions have something to do with closure properties. This one has to do with something to do with undecidables. You have to answer whether something is decidable or not. And then part D is something to do with a regular grammar. Okay? Then the, is that 5? Oh, I have only 7 parts. I need to put another one. I just realized that. So the fifth one, I guess, is something to do, again to do with undecidability. Same with the sixth, and then the last one's something to do with PDA to CFG. So remember, keep the answers brief because some people lost a lot of time on the first test because they wrote way too much on this one. So I'm only expecting like 1 to 2 sentences on each. Just write what you need and move on. You don't need to spend a lot of time on this. Just write whether it's true or false. If it's true, just give a very brief explanation of why it's true. And if it's false, give a counterexample because that's what the directions say. Yeah.
For that counterexample, let's say suppose it's a lemma or something, we can just mention it.
Yeah. Yeah, unless that literally is the question. But if it's not like for example, this is not one of the questions, but one could be every context-free language is regular. So what would a counterexample to that be? 0 to the n, 1 to the n, and at least 0. Done. That's 5 points immediately. So yeah, just answer counterexample if there is one immediately. Any questions about first question? Okay. Question 2 is a little bit familiar, something to do with prove or disprove. And so these 2 parts will be something that realistically you could be concerned about relative to regular languages. So like your boss may ask you to solve one of these problems or show that you can't solve it, that sort of thing. So hopefully these won't be too hard, and they're based on the problem sets that you've seen so far. Third question is a little interesting. So the first part is I'm going to give you a sequence of arguments that your boss may tell you, and there's something definitely wrong with the statement because it'll have something to do with the B part. The B part will contradict the argument in part A, and then in part A you just have to say why the argument's wrong, and then part B obviously has something to do with the pumping lemma. Okay? Not for CFLs, so it's not on anything that we're doing today. So it must be on regular languages. Yeah.
So 3A is itself divided into 2 parts?
No. Part A is just one argument. Say why the argument's wrong, and then part B will contradict what the argument is. So therefore, that shows that the argument's wrong. So therefore, you have to prove part B. Any questions about
So for like on the last piece that we did, the pumping lemma had a ton of cases
Mm-hmm.
to prove it wrong. Can we expect something that's like a little bit
We'll define a ton of cases.
more than I wanted to write on the test?
Well, there's actually I'll guarantee that there are not many cases, but it's not going to be a completely trivial question. So, but it'll just involve the same basic structure argument that you've seen before. But in most of the cases, if you have a lot of cases to deal with, you can actually boil them down to a simpler argument. And the problem set solutions will actually show you one of those for that particular question. Other questions? Okay. That's number 3. So the last 3 are stuff you probably will expect. Part A, make a regex. Part B, convert it to an NFA. Part C, convert that to a DFA. So nothing out of the ordinary. And I'll make sure that the NFA and DFA are not big like the recitation was. My bad. Yeah. Oh, I misspelled question. I need to fix that. Something to do with CNF, and don't answer what it is, but you can probably guess what it is. And then part B is something to do with the PDA. Okay. So on to question 6. Question 6, which is bonus points in some sense. Can make a DFA for some language. Part B, convert it to a regex. Super easy. Well, straightforward. Any questions about the test? Yeah.
If you happen to get over 100% on this test and it would replace your previous test with the higher than that.
Well, that's the stated policy. So, any other questions? Yeah.
Could I see page 4 and 5 again?
Why?
I'm trying to take notes on what I need to say.
I'm No, I'm very hesitant to do that.
Do it.
No. But I should mention, I'm giving you an entire page front and back of rough work. If one side was not enough last time, I'm giving you a whole page this time. And of course, any amount of notes like last time as usual. Any questions about the test itself? Yeah.
Anything about what you studied before the exam?
Well, I'm not going to, well, as you can see by the questions, I'm not going to explicitly ask about it, but I'm not going to ask you like, show that ETM is undecidable or whatever, but you might need to use that knowledge in order to show something. Yeah, or, well, like you saw a few of them. You need to know what a decider is, like things like that. But I'm not going to explicitly ask, like, what's a decider? Yeah.
The exam length is still 75
Mm-hmm.
minutes?
Yep. Yeah.
Are we allowed to use problem set solutions for our notes?
Yeah, sure. I said anything, so as long as you don't disturb your neighbor, I don't care. Yep. Other questions?
Does that include the textbook?
Yeah. I said any written material, so I guarantee you'll have never seen these problems before. So, any other questions? Yeah.
Are we having lecture after class?
Yeah, yeah, we're having a lecture after. Yeah. Unless we go pretty far today, then I might not, but because we're quite ahead. But we'll see how far we get today.
Start going.
Any other questions? Yeah.
So this covers up to everything Friday?
So what's the answer to that question? Yes.
Thank you.
Mm-hmm. Other questions? Okay. So let's get back to business unless there are like problem set questions. What's that? The TA I put on office hour said it's going to change office hours this week to Monday, Tuesday, Wednesday. But are you asking for my? I don't have office hours tomorrow, but I will later, obviously later tonight. So after class, yeah. Hey guys, shh. I can't hear you. I still can't hear you. Oh, yes, you're absolutely right. Thank you. My bad. You're totally right. Other questions? So let's actually, if you remember from, I think, 2 lectures ago, we tried to assemble where we are so far in terms of language classification. So we talked about several different types of languages. So we talked about decidable languages, and let's say that that encompasses this bubble. And along with decidable languages, what types of other languages did we talk about? Well, yeah, but like instead of something, like what is like a recognizable? Yeah, a positive term, I guess. So why am I putting recognizable out here?
There are more of those.
Right. So we showed that every decidable language is recognizable from the definition. Can you come up with a recognizable language that's not decidable? ATM is obviously one of them. Of course, there are many others, but that's one of them. So we know that there are some languages out here. What about some way out here beyond even recognizable? ATM bar is definitely one. Another one that you might consider is EQTM. But there are many, many, many languages out there. But we decided that when we're talking about these types of languages, the model is way too complicated, right? ATM, ETM, every single problem we can find about Turing machines pretty much was undecidable. So what did we do after that? What did we do to the model? Instead of talking about Turing machines, we talked about DFAs. by simplifying the model, then we can get the problems to be tractable now, or decidable. A DFA, E DFA, all of those problems we found were decidable. And what are the languages of DFAs? Regular languages. And for that reason, every regular language is decidable. So let's put regular in here. And we talked about various different models for regular languages, DFAs, NFAs, regular grammar, and regex. And then what did we do when we talked about regular grammars? We tried to generalize it to what? What did we call those? What kind of grammars? Context-free grammars, right. And what are the languages of context-free grammars? Context-free languages. And because every regular grammar is a context-free grammar, what can I tell you about or what can you infer from the regular languages versus the context-free languages? Right, the context-free is a bigger subset of that. But where does it fit? Where do the context-free languages live in this hierarchy? Are they below decidable, or do they go beyond decidable, or what? Or is it just in between, or what? It's actually in between. And how can I convince you that that is true? Right, the ACFG we found was decidable because we talked about C and F, and then we can just try all 2n-1 ways to apply rules. And then, therefore, we can check whether a grammar actually generates something. And then we talked about PDAs, and then last time we showed that, in fact, they're equivalent too. So what's a context-free language that's not regular, as an example? The 0 to the n, 1 to the n is perfect for this one. Another one that we saw was balanced curly brackets. I call it curlies. So we found context-free languages that weren't regular. Is there one that we haven't, in any one of these layers, we haven't found an example of a language yet? Decidable but not context-free. So in fact, that's one layer that we haven't figured out yet. So let's try to figure out how would we find a language out here. Well, consider this language. So it's like 0 to the n, 1 to the n, but I'm going to make it a little bit more complicated in some sense. So instead of 0 to the n, 1 to the n, I'm going to have a 2 to the n as well. So what the strings in here are, some number of zeros at the front, then the same number of ones follow that, then the same number of twos follow that as well. Okay? Why might this be hard for a, let's say, PDA to recognize? Well, what was our idea to recognize 0 to the n, 1 to the n for a PDA? Yeah, we put the zeros on the stack, and then what did we do with the ones? Yeah, we just, whenever we saw a 1, we just matched it up with the zeros on the stack, and if it matches at the end, great, then we accept. Why might it be troubling here? Exactly. So if I push the push the zeros on the stack like before, then I see 1s. Then I'm going to match them up with the zeros at the end, at this point. Then I still have 2s left over. Well, how am I going to match them against the zeros that are now popped off the stack? Is that a proof that this language is not context-free? No. It says that that particular method won't work, right? Maybe there's some other clever method that could work. Remember the same number of 0 1s as 1 zeros language? So just because a DFA can't count, that doesn't mean a DFA can't recognize that language. So in fact, there may be some other crazy method that works. But in fact, we'll show that no such method exists. Well, maybe we can try, right? Maybe we can try. Well, suppose that we could make a CFG for this. let's call this language L. So let's suppose L has a CFG. Maybe we were just wrong in saying that it doesn't have one. Maybe it actually does. Let's see. So let's look at a string W in L. Okay? So let W in L. Okay? Just pick any string in L. So it's some number zeros to the front, then ones, then twos. It actually doesn't matter. But let's just pick a string in the language. What do I know about that grammar if I want to generate that string? Can I generate that string? Yeah, how can I? How do you know I can generate that string? Well, yeah, there's a CFG for the language. So there must be some way to generate the strings that are in the language. And we said that W is an L. So there must be a way to generate W. How can I convince you, what can I show you to convince you that it really could generate W? I can show you a derivation, or what else can I show you? 2 words. Parse tree, right? If I show you a parse tree, would that be enough to show you that W is an L? Yeah, because then I can just look at the leaves and then look at the internal nodes of the tree and see, oh yeah, you applied this rule right here, and you applied this rule here. And if you get exactly W on the leaves from left to right, that's a parse tree. What was the idea for showing that some kind of things repeated for the DFA when we talked about the pumping lemma for regular languages? What did we do for the DFA to get more strings in the language? So we picked a string in the language, and then what did we do? What was there?
We decomposed it.
Well, we decomposed it, but what did we have to guarantee about the string itself? That at least equal to some length, right? Well, what do we want to repeat here? Well, let's see. I can't repeat terminals because I have a fixed string that I want to make. I want to make W. So what could we repeat instead? Well, what is in at the top of the tree of any parse tree? What's at the very top? A start variable, right? For any arbitrary grammar, what do I know is at the next layer? Do I know anything? No. In fact, all of the terminals might happen to appear after one rule application. There may be no more variables at all. That sounds like a problem, because now if I look at an arbitrary string, the way that this tree is structured will depend on what the string is, not necessarily on maybe like the length of the string. Well, is there something that we could actually do to guarantee something about the first layer below the start variable? What if they were all variables? Then maybe we can say that the second layer is all variables, then the third layer is all variables, and then all the way down until we reach the leaves at the very bottom. Well, could we convert this grammar into CNF? Yeah. Well, let's suppose that just without loss of generality, this grammar, whatever it is, happens to be in CNF. Okay, well, maybe now we can say something about what the tree looks like. Well, as before, we know the start variable's at the very top. That never changes. What's one level down? If I apply one rule with S and W say long enough, what is the first level after the start variable? 2 variables. So let's just call these, it doesn't really matter, but let's say that there are 2 variables here. And again, let's say the string's long enough. What about the third layer? It's going to be 4 variables, or most likely it's going to be variables. Some of them may be terminals, but the nice thing here is that the tree is binary. If we take the leaves off the tree, so let's just say that this generates, so let's say that this is a variable, and this generates, say, wn, the last character. And then if we look at the tree other than the leaves, just take the leaves off the tree, what do I have left in as the tree structure itself? Well, let's see. Every single node in this tree is a variable. So, and what do we know about the children of any node in this tree? It must have two variables other than the now leaves of the tree, right? Oh, so this tree is binary. So the parse tree now is binary. Well, it depends on the derivation that we come up with. Maybe the leaves are not all at the same level. Maybe that some of them are higher up, some of them are lower. We actually don't know because it depends on the derivation that we consider. But let's actually consider the case where they're actually all at the same level. It actually won't make a difference. So let's see. So start variables up here. So now let's draw what I call an artist's conception of a parse tree. So that the tree may not actually look like this, but let's just suppose it happens to look like this. And then at the bottom, it makes all the leaves, which happen to be the terminals of the string we want. So in this case, it's W1, W2, all the way to Wn over here. And we know, of course, if we take the leaves, these Wi's off the bottom, the rest of the tree is just entirely full of variables, and it's a binary tree. Questions so far? What if I made this string longer? What happens to the tree? Well, obviously more leaves, but can you guarantee anything else about the tree? Ah, the tree gets taller. Well, wait, let's think about that. If I make the string longer and longer and longer, could we just have a tree that's just at the same height and it never grows taller? No, why not?
It's a binary tree.
It's a binary tree. Well, even if it was an arbitrary tree and I guarantee something about the number of children of each node. Well, let's see. At the first level, there's one node, obviously. At the second level, how many are they? How many vertices in this tree are there? 2. And then it doubles at every iteration. If the number of levels is, let's just say, h, then how many are at the last level? 2 to the, well, it depends on how you count, but let's just say 2 to the h, for example. It depends if you count the last layer or not, and it depends where you count from, but let's not deal with the issues there. Well, how many nodes is this in total? Well, isn't that just 2 to the h plus 1 minus 1? Well, let's see. If I have a string that's longer than that, what happens to the height? It must be at least h plus 1, right? Why does that have to be the case? If I pick a string of that length plus 1, then let's see. Could I have a tree of height h? No, because I need more leaves than there are nodes at the last layer anyway. Even if it was a complete binary tree, then I still need another node in the tree. So therefore, I must have another layer. Okay? What kind of principle is that called? Pigeonholes? Pigeonhole principle. Ah, so that must mean that by the pigeonhole principle, at some point, if I make the string longer and longer and longer, the tree grows taller. What did we want to repeat again for the grammar? We wanted to repeat, we can't repeat terminals because we have a string to work with. But We can repeat variables. Well, if I make the tree taller and taller and taller, will there be some point where if I go from the top to the bottom, it will have more variables, like say n plus 1 variables that I'll see along the way, and there are only n variables in total? That means I repeated a variable. Well, let's actually look at that. So suppose that suppose W is at least this number plus 1, which is 2 to the h plus 1. Okay, well, let's see. That must mean, actually, no, that's, we need to make it explicitly the number of variables plus 1. So let's say number of variables plus 1 out here. So let's see. This says that from this part, that says that the tree must have height at least h. Because if it was a complete binary tree, then that means that I have at least the number of variables, number of layers. Then this plus 1 at the end tells us we must have another layer. So of height at least the number of variables plus 1. So if I just look at an arbitrary path, say this one, from the top to the bottom, and I just look at the variables along the way, am I guaranteed to see number of variables plus 1 number of variables? Like if there are 10 variables in the grammar, am I guaranteed to see 11 variables along the way?
No.
No, why not?
You just keep hitting the same variable.
No, but then I see a variable repeated. 11 occurrences of variables is what I mean. Well, no, this is an artist's conception of a tree. It may be that the first terminal is generated way up here. And if I chose the path wrong, that means that I can get a really short path and not see a repetition of a variable. So what should I look at in this tree instead? If I look at the longest root to leaf path, am I guaranteed to see n plus 1 variables? Yeah, because of the pigeonhole principle. There must be some, if I made this string this long, there must be some variable that's deep enough to guarantee a repetition from the root down to that variable. Whatever it is, I don't know what it is, but some variable has a repetition. So let's look at the longest, or a longest, I guess, root to leaf path. And let's suppose, okay, let's suppose it's, actually I'm going to remake the tree to be a little bigger. So let's say it's, because I'm going to need some room for this. So S is up here. And let's say that we looked at the longest root to leaf path, which is this one. It may not actually be in the middle. It may be off to the side or something like that, but let's just imagine that it's in the middle for now. Well, let's see. Could S be repeated on this path? No, why not? It's in C and F. So that means after the top, that first layer, S can never appear again. So, but some variable, since I guaranteed the height of the tree to be large enough, some variable must have repeated along this path. Well, I don't know where those variables appear. So let's just say that one occurrence of it is here. This variable is not the start variable, but it actually doesn't matter. And then the second occurrence is here. This variable, of course, could appear many times. Just like for the DFA, we could see the same state over and over. But I guarantee some variable appeared twice. That's all I can guarantee. Could A generate the empty string? This variable A? No. How do you know that? It's not the start variable. See how C and F is very powerful? So we can actually guarantee something about the variables that are generated here. Well, I don't know necessarily what they generate, but they must generate something of the string. So let's say that the lower occurrence of A makes this part of the string, and then the middle occurrence may make a little more of the string. And then let's label each of these parts just like the DFA when we talked about decomposing it earlier. But now we're going to decompose the leaves of the tree here. Well, how many parts are there here? Well, let's see. There's 1 here, 2, 3, 4, 5. Looks like 5 to me. So let's actually label these with 5 names. So instead of 3 before, we're going to talk about 5 here. So let's call them U, V. If my U's look too much like V's, just let me know. Then Y, then Z. So instead of just X, Y, Z, we have 5 instead of 3. Let's see. Well, now we just need to guarantee some properties about other strings in the language. Well, let's see. Is this a context-free grammar that we're dealing with? Yeah, it is a context-free grammar. So if I was mad enough, and I am, if I just copied this higher occurrence of A, and I just copied it down to where the second occurrence of A is, am I going to get another string? Yeah. Well, let's see. Let's see what that even looks like. So if I copy this down, then I'm going to get this. I'm not very good at art, as you can probably already guess by now. Well, if we just delete the parts in between, well, what do we know about the leaves of the copied version? What do we have on the bottom of that part? We have VXY again. So that means we have VXY. Oh, that must mean we have another occurrence of A. Because of the second occurrence of A, we copied it down. So now in fact, we have 3 occurrences of A. So let's say it's there. And then this path again. Let's say it's there. And then, of course, the lower occurrence of A still makes X, just like before. Well, let's see. Could I keep doing this process over and over and over? Oh, so what can you tell about like what strings are in the language? Is U, V, so 2 copies of V, X, 2 copies of Y, Z. Did I just make a parse tree for that string? Yeah, because look at the leaves from left to right. I have the U part here, then 1 copy of V, then another copy of V, then X, then Y. Oh, I should have another Y here. A second occurrence of Y, then Z after that. Oh, that's the string I have. What about U, V, 3 V's and 3 Y's? Can you guarantee that's in the language? Yeah, and what we do, we just do the copying thing again. What about UXZ? So 0 copies of V and Y. Well, let's see. What if I just take the this little occurrence of A right here, and I just move it up to where the original occurrence of A was. So the tree now looks like this instead. It actually doesn't look like quite like that. It'll look like, so you got failed art. It'll look like this, or something close to this. So the 1 occurrence of A is here, and it makes this part of the string. Well, that means that the U part's here, the X part, because we copied it up, and the Z part's still over here. Oh, did I just make a parse tree for that? Oh, so that must mean all 3 of these are in L. Can you see a pattern? Oh, what's the pattern? So what are the things I'm putting the I on here? V and Y. The same number or a different number? Same number. Why? Because we're copying them in tandem. So the same number of copies of V and Y. So from this we can deduce that if we put the same number of copies of V and as Y, then we're always going to be in the language. Sorry? We're going to get to that. But you're right, yes. Any questions on that reasoning? Okay. So as was suggested, what did we talk about for regular language when we talked about the DFA? Well, we saw that for the part that had the loop in the DFA, we must incur at least one transition. So we deduced that the part that we have multiple copies of, that part had to be non-empty. So what are the parts in here that are being repeated? Instead of just one, how many do we have in this case? Two, the V and the Y part. So now we need to just figure out which ones could be empty, which ones have to make something. Okay, so let's blow this up a little bit. So let's say that this is the first occurrence of A up here, and then obviously this is the second occurrence of A. And of course, this makes something, this makes something, and this is the VXY part. Well, let's see. Well, we can actually guarantee something about the X part here, but we actually don't need it. Well, whatever the second occurrence of A makes, could the first occurrence of A make the exact same thing that the second one does? In other words, that V and Y are both empty. Could that be the case? Well, how far up could the second occurrence of A be after the first one? Could it be right after it? Yeah, certainly. So let's actually look at that case. So here's the first occurrence of A. Second occurrence of A is right here. And then the other side is some variable. It may be A also, but it's just some variable. So let's see. The first occurrence of A's sub-parse tree is going to look like this. And then it goes over here like this. And then, of course, the second occurrence of A is going to have some parse tree that looks like this. So what does this parse tree tell you about V in this case? It's empty, right? Because the variable A could coincide with one side of the parse tree. Could it coincide with the other simultaneously? No. So what do you know about this part over here? It must be non-empty because we know that this variable cannot be the start variable. So could it make the empty string? No. So in fact, the other side of the parse tree of the sub-parse tree that we don't consider, that part has to be non-empty. Whether the one side is empty or not, the other one has to be non-empty. Okay? Well, could it be that the Y part is empty and the V part is non-empty? Yeah, because we can just flip the picture around. Oh, so could V and Y both be non-empty? Non-empty. Yeah, because if A appears lower than right after the first occurrence, then certainly both sides are going to have to be non-empty. But it can't be the case that both of them are empty. Okay? So in fact, a way to say this is that the length of VY together is at least 1. So that means that at least one of them has to be non-empty. It can't be the case that both of them are. Okay? This is the part where some students struggle, so ask questions if you're confused. Yeah?
Can you explain that again? I'm quite clear why.
Yeah, so we're just trying to say something about the v and x, vxy parts, right?
Yeah.
So, so what we said is, well, it could certainly be the case that, actually it is the case, if we look at the first occurrence of A, then it can't coincide with what the second occurrence of A makes, because because the first occurrence of A can't make the empty string, right? Or any occurrence of A. So that must mean that right off the bat, that V and Y together have to be non-empty. One of them has to be non-empty, or both, possibly, because the two occurrences don't coincide together.
What do you mean by coincide?
So like these, at least one rule application occurred between the first and second occurrence. They're not exactly in the same place in the tree. So that must mean that since they are at least one rule application apart, then the other side of the subparse tree right here, this variable b, that must generate something, because b is not the start variable and therefore can't generate the empty string. And so therefore, one of the, even if it coincides on one side of the parse tree, it can't on the other side, because the other variable has to generate something.
Okay, you said the B can't produce the empty string because it's on
Right.
the start. But I thought in Chomsky normal form it could produce an empty string.
But remember, the rule said that the rule has to be of the form a variable makes two variables, where b and c are not the start variable. And so here a makes, in the worst possible case, it makes a b, but then a and b cannot be the start variable, which means b cannot make the empty string.
You just have a B that makes the empty rather than A to B, C.
But then it's not in Chomsky normal form.
Is it not? I thought Chomsky normal form was A, B, C.
Yeah, I reproduced it right here. A goes to b, c, but b and c cannot be the start variable.
Oh, okay.
Yes, and so therefore, well, a can't be the start variable no matter what, but b is all we need to not be the start variable, because now we can guarantee something about this part, and we can guarantee it's not empty, because b has to make something, because it's not the start variable. And if the second occurrence of a occurs lower in the tree, then both are going to be non-empty.
So it all relies on
Actually, no, that's not true. But
binary part.
oh no, that is true. Go ahead.
Since we're giving B some space to do something, it
Yeah.
has to make something.
It's not because it's binary. It's because it's in Chomsky. The grammar's in Chomsky normal form, and so we can guarantee something about the variables in the tree. That's the key here. Yeah.
Can you explain why it can be empty on the left side?
Because we could have a rule like this, right? A goes to AB. That's certainly allowed, because A and B are not the start variable. So if we look at if that happened in the parse tree, then the sub-parse tree right here that's what it would look like. Well, that must mean that on the left side of this first occurrence of A, then the left side of the first occurrence of A has to coincide with what the second occurrence makes, because there are only two children of the top A right here, right? Because there are only two children here. So whatever the top A makes is whatever the second occurrence makes combined with whatever B makes. So the first part of the top occurrence of A must match with what the second occurrence makes, right? Because there's no other way that the top occurrence can make anything else other than what the two children can make. And so that's how the top occurrence and the second occurrence can coincide on one side. But the other side, they can't coincide, because I'm looking at one path through the tree. I can't look at a split like this, right? So that must mean that some variable, whether it's A or not, that second occurrence that I did not consider must make something, which is the right side in this case. If I flip the picture, then it would coincide on the right side, but something on the left would have to be non-empty.
What happens if you make B A in that case?
Well, a good question. So if I did that, which is certainly allowed, remember I'm only looking at one path through the tree. So it's going to go through one of the two sides, right? But then the other side has to make something because it's not the start variable. So that's why one of the sides has to be non-empty for sure. It could be both are non-empty, but one of them has to be. Good questions. Any other questions? Okay, so what was the other thing about the regular language pumping lemma that we had to consider as well? So we looked at if we just pump this middle part many times, and then we saw the middle part couldn't be empty, but what else did we see? Well, we saw that the first two parts, the x and the y part, couldn't be too long, right? The length of xy is at most this constant, right? Well, maybe we can do something similar here. Well, let's see. So let's look back at this. The constant actually isn't important, but let's suppose we make a string that's exactly that long, right? Let's just say that we make a string exactly that long. Well, does all of this analysis still apply? Yeah, just like the regular language case. Same thing here. Well, let's see. How long can the part that's being pumped be? Well, what's the part that's being pumped? Well, the part that's being pumped is the VXY subtree, right? Because I'm doing these copies. It's the VXY part. So what we want to know is this. How long can VXY be? Because that's the part that I'm actually pumping. X isn't really the part I'm pumping, but I'm taking it along for the ride because I'm taking the subtree and I'm copying it down. Well, let's see. Well, if I take any subtree, so let's say I have a really big I'm making a lot of parse trees today. So if I make a tree like this, and I take a subtree like this, any subtree at all, where it goes all the way down to the leaves, and I guarantee that this is at least p, that constant from earlier. So if I guarantee that whatever this subtree is makes at least p characters of the string, do I still have this repeating variable pattern? Yeah, because because of the pigeonhole principle. But even if I make the entire tree have the leaves be of length exactly p, then I still see the pattern. So if I imagine that this is like a little parse tree inside this larger one, then I still see this pattern. Well, let's see. If I just consider now whether or not I look at this tree as the entire tree. So let's say that this is equal to p in length. This is the top of the tree, the entire tree. This is the bottom. Well, how high up could these two occurrences be? Well, they could go almost all the way to the top of the start variable, where the start variable is, right? Well, let's see. So let's say that they're right after the start variable. It actually doesn't matter, but let's see. The VXY part is generated by what variable? The one of the A's, namely the top one. So let's see. The top part of A is going to make something like this. Could the top occurrence of A in this situation make more than p characters? No, because the entire string is p characters. Well, if we went back to our larger picture here, and I just looked at this little parse tree where it makes exactly p characters, or at least p characters, then what has to happen? If I look at the top occurrence of A here, then it can't make more than p characters by definition. But the key is where, if I look at this big parse tree now, the issue may be if I pick the wrong variables to look at. So if they're way up here, could this top occurrence of A make more than P characters? Yeah, because I'm looking at a big parse tree. I said if I look at a little parse tree, then I'm okay. But if I pick repeating variables on this big parse tree, I can't guarantee anything about the length of the top occurrence of A, right? Of course, it's less than the length of the total string, but I need to pick a string of length at least P. So what could we do? How about let's look at the lowest repeated occurrences of a variable, of that variable A. Well, if I look at the lowest occurrences of this repeated variable, let's say they're here, could the top occurrence of A make more than P characters? Well, let's see. If we look up at most V plus 1 variables from the bottom, then we must see a repetition, correct? So that must mean that by definition, the subparse tree where that one is must have this repeating variable pattern. And then we get all the properties like before. So if we look at the lowest repeated occurrences of some variable, then we're okay. Which means that a variable here, the top one, can't generate more than P characters. So what could we guarantee about the length of Vxy now? It means it's at most P. Because now we can find where the variables are that help us find where this repeating pattern is, and it's not too long. Because we just look at the lowest repeated occurrences of the variables. So by looking at lowest repeated occurrences of any variable, we guarantee that Vxy is at most P. Cool. So we can actually state the pumping lemma for CFLs here. So, because we actually have all the pieces that we need. So, how did the pumping lemma for regular languages start? What do we have to assume about a language first? That it's regular. So, in this case, we're going to let L be A. Context-free language, yes. Can I use the pumping lemma in either case to show that a language is regular or is context-free? No, why not? Because I have to assume it first. So I'm assuming the thing I need to prove, which is a red herring. So we're going to let L be a CFL. Then what do you think comes next? There's this constant P for L. So then there exists a pumping constant P for L. So it's almost identical to regular. Well, what strings do we need to look at here? It's the same two criteria, which are longer than P and in the language. Why do we need to look at both of them here? We'll see. If I guarantee that it's in the language, what do I guarantee about the grammar? What could it make? Could it make a parse tree? If it's not in the language, could it make a parse tree? No, because a parse tree coincides with the strings that it can make. So being in the language guarantees you can make this parse tree. And why do we say at least P characters in length? Right, so we can have this repeating pattern. Okay? So it's analogous in every way to the regular language case. So such that for all strings in the language, meaning it has a parse tree, with length at least this number, which means that we can now guarantee there is a repeating occurrence of a variable, then there is some way to break it up into 5 pieces. I'm not saying every way works, but some way works for all WNL such that with W's length at least P, with some decomposition, W is U, V, X, Y, Z. And the 3 conditions. So the 3 conditions are, we showed that the middle 3 pieces can't be too long because we just looked at the lowest 2 repeated occurrences of a variable, which means we can guarantee is at most this certain constant. So the VXY part, the middle 3 pieces, which are the pump pieces, are at most P characters. Then we saw that, or I'm doing it backwards, but we saw that if we looked at the parts that really are pumped, the V and the Y pieces, then one of them must be non-empty because the second occurrence of the variable can't coincide on both sides with the first occurrence. So that must mean that one of them is non-empty, i.e. the length of them together is at least 1. And then at the very beginning, we saw that if we pump the V and the Y pieces at the same time in the same number, then we'll always get a parse tree for that string, i.e. it's always in the language. So that means that U, V to the I, X, Y to the I, Z is in L for all I. So it's very, very analogous. But the only difference here is that we have 5 pieces instead of 3. And now the middle 3 pieces, the things that we need to look at for pumping, could the VXY part be at the end of the string? Yeah. Did I say anything about the substring U? No. So here, the part that you're going to be concerned about is not necessarily the prefix of the string. It can appear anywhere in the string. Okay? So now we just need to consider, when we try to use this, we need to look at the entire string all the way through and see, could we pump out in any of those cases? Okay, any questions about this? Yeah.
So, if I is 0, say I is 0, does it handle the case where no variables is repeated? Yeah, exactly. Yeah, that corresponds to 1, or even if there is a repeated occurrence, we just delete the we just move the second occurrence up to where the first one is. So effectively, we're deleting the V and Y part. There could be other repeated occurrences, but we're deleting one of them here. Any other questions before we break? Right, it breaks it because you can choose the decomposition. V is the last 0, X is empty, and Y is a single 1. And then you can just repeat that, add more zeros at the front, add more 1s at the end. So in fact, that wouldn't work here. Any other questions? Okay, let's take a break.